it's a great honor to participate to this Yahoo conference, and I will speak about the question of linearity or non-linearity of subgroups of automorphism of the plane. So first of all, let me remember what a linear group is. You take an abstract group, and you say that G is linear if G can be embedded into some matrix group, G and K, for some n, some integer n, and some field K. So from now on, this symbol means can be embedded. It's not an obvious conclusion, okay? And many authors show that the automorphism group of manifold share properties with linear groups. And there have been many works on that topic. The last work up to date is a preprint by Bezushak, Petravchuk, and Zelman. But here I ask the following question. Are these groups, especially the group of automorphism of the plane, are they really nonlinear, even if they share properties? And what I would like to explain is that if I take the automorphism group of the n-dimensional space over a field K, then even if I take, and I look at large subgroups, inside this, and basically what's going on is the following. For n equal 1, this group is linear. For n at least 3, even large subgroups, to be more specific later on, are not. And the interesting case is a case n equal 2. And n equal 2, it is a kind of chaos. But sometimes the chaos is interesting in mathematics. So let me be a little bit more specific. So K is a field of A to K. So A to K means the affine plane of dimension 2. And you take polynomial automorphism, so it is given by automorphism phi of the form xy goes to f of x, y, g of x, y, and where f and j are polynomials, and you should have a polynomial inverse. Now let's define some big subgroups. So the first big subgroup I have in mind is what I call pot 0 of A to K, and there are exactly the phi such that phi of 0 equals 0, from the initial point to itself. And in some sense, I will not be very precise. You should take it as an informal definition. This has to dimension 2, because the quotient is a affine plane. I can also define S of pot 0 of A to K, which is the same set phi, so that phi of 0 equals 0, and in addition, I want the Jacobian of phi to be equal to 1. So take polynomial automorphism which preserve the volume. But since the Jacobian is always a constant, it's an invertible polynomial, so it's a constant, indeed this is the same as maps automorphism phi, and that's phi of 0 of 0, and the differential of phi at 0 is the identity, belongs to SL. And because of this description, you see that this group has somehow has 3-dimension 3. And I will need another group, okay, which is port 1 of A to K, which are all automorphisms phi, so that not only it sends 0 to 0, but also the differential of phi at 0 should be the identity. So now these are the three groups I will work with right now. And I will now state the first theorem, which is the following. Theorem A. So it contains two components. A1, which is not very surprising, it says that if K is infinite, the infinite field, then this group S hot 0 of A to K is not linear. Usually you expect that this kind of infinite dimensional groups are not linear, so it's not a surprise. But the statement A2 is more amazing. It says that there is an embedding of the automorphism group of port 1 of A to K into SL2 of K of A. This means that you should add to your field one indeterminate, and you have such an embedding. And first of all, let me explain some corollary of that. Is that if K is finite, so it's the converse of A1, the field K is finite, then the whole automorphism group of A to K is linear. Again, linear over K of T. And the reason why is because if K is finite, this group has finite index. So finite index. So whole group is linear. Now I would like to show that these results are very specific to dimension 2. So specific. And so I would like to show that in higher dimension, you have never linearity results. So for my purpose, it will be enough to look at the case n equals 3. And now I would like to look at groups inside the automorphism group of the space of dimension 3. I would like to look at groups which looks a little bit like port 1 of A to K, and maybe even much more general. So to do so, I take any finite n-dimensional ideal in the ring of polynomials in 3 variables. And I will define out M of A in K as a set of all automorphisms of in dimension 3 such that phi of x, y, z is equal to x, y, z modulo of ideal M. So for example, I see on my screen that there are 27 auditors in the room. So let's take for M the ideal x, y, z to the 27. And in that case, out M of A 3K are all automorphism phi such that phi equal x, y, z is the identity plus the big O of 27. So you see it's a generalization of this out 1, where out 1 was x, y, z plus a big O of 2. And the theorem says that for any M, or any finite codimensional ideal M, the group out of K K is not linear. And this is including the case where K is finite. And you see that huge difference between dimension 2 and higher dimension in the sense that in higher dimension anything of finite codimension in a reasonable way is not linear. So now I would like to turn my attention. So now I will only speak about dimension 2, and I would like to turn my attention to finitely generated subgroups. And for that, I will assume that K has characteristic B, a characteristic 0, sorry. And let me describe a subgroup, gamma, with two generators, ST, which lives inside, say, the automorphic group of the plane of Q. And this group is defined as follows: S of xy is simply the linear transformation y to x. It's a very simple transformation. And T of xy is the transformation x and y x squared. So it's extremely simple automorphism. And now we will say it's theorem C, sorry. So you see that gamma indeed sends 0 to 0. So K is any field of characteristic 0. And so gamma can be viewed as a subgroup of automorphism 0, those because of the field of over any field. And theorem says that the theorem C1 says that this group is not linear. A very simple group which is not linear. And statement C2 says almost the opposite. It says that any finitely generated subgroup of now S, if you add the condition that it preserves volume, is linear over some extension of K. So you see, this is very strange because this is a subgroup of the dimension 3. We have seen that this group is not linear, but any finitely generated subgroup is linear. And now I would like to make some comments about C1. Indeed, as an abstract group, the group C1 is the group gamma, has the following presentation. So it is generated by two elements, sigma and tau, and only one relation. Sigma square tau sigma minus 2 is equal to tau to the square. And this abstract group as an abstract group appears in a work of Drutu and Sapir. No, yes, Drutu and Sapir. And they claim that it was the first one relative group which is not linear, which is non-linear, but basically finite. And so what C1 said is that this group, this abstract group, can be realized inside the group of automorphisms of the plane. But the good point of that C1 implies that the following. You see, the two generators are defined over C. So C1 implies that the group gamma acts over the plane x squared of any odd p and faithfully on their product over all odd prime numbers. And therefore, it is obviously reasonably finite. And it's interesting because the fact that this group is reasonably finite, this has been established by Borisov and Sapir using some dynamical systems, some dynamics. Famous and complicated paper, and here you get it almost for free. The fact that it is not just reasonably finite. Now, I would like to come to the last theorem, but I would like to make a comment about C2. C2 is based on building a certain ping-pong setting in some big representation of the Lie superalgebra OSP12. So it's a mixture of Lie superalgebras and kind of dynamics, ping-pong lemmas. But I will not explain that. And of course, usually the dimension, the degree of the representation are extremely high. So now I would like to come to the last statement, which is as follows. Remember that S of 0 of A to K, this one, so I will assume now that K is infinite. This one is not linear. And it contains, as a subgroup, those which are 0 to 0 and with differential identity, which is linear. So indeed, the core of my paper is to understand what the linearity property, the linearity or non-linearity of intermediate, of any group between. Between these two groups. And it's very simple to understand what are these groups. Groups which are between are groups that I will denote out S of A to K. So they are classified by subgroups of SL2. And they have the following form. They are all 5, a group of all automorphisms, so that 5 of 0 equals 0, and the isotropy, the differential of 5 at 0, belongs to S. And the question is, for these groups, which one are linear and which one are not? Because I want to understand how you go from non-linear to linear one. And basically, I need to introduce a new notation now. So if delta is an element of the projective line, the line of the space of dimension 2, then I denote by S delta is a fixator of the line. S, of course. And of course you have a map, a stupid map, from S delta to the linear group of the line. But this is a one-dimensional space, so this is isomorphic to K star. And you denote by lambda delta, which is a subset, a subgroup of K star, which is the image of this map. So for each delta, we can define a subgroup in K star. And right here, and there are criteria for linearity and non-linearity. For linearity or non-linearity, which are based on the structure of lambda delta. But these statements are quite technical, so I will not explain it into details. Just say that it's almost give an exact answer, but not exactly. The only problem terms is in the understanding of roots of units inside the lambda delta. So it's up to some details, it almost gives a complete answer. But instead of explaining a very complicated criteria, I would prefer to give one example. And the example is the following. So it's example A. Which is the following. So I take Q equals Q of xy, be a quadratic form. Okay. And I take S, be the orthogonal group, SO of Q. And the statement says the following. A1. If Q is an isotropic, then this group put S of A to K is linear. An isotropic means that Q has no zero, except 0 of course. And the opposite statement is otherwise it is not. So even in this example, we see some chaos because we go from nonlinear to linear with some very small changes. And I would like to explain a few examples. For example, if you take which one? If you take S equals SO to R, so here I mean the quadratic form is x2 plus y2, of course. Then this group put S of the plane, of the real plane, is linear, but indeed it can be embedded into SM7 of C. Another example, if characteristic of K is, say, 31, and Q an isotropic, okay, and the proof shows that the automorphism group of S of A to K, so here it's the field is R, can be embedded into SL64 of KOT. So this is just to explain that the proof is not uniform. It depends on the characteristic of the field. So in characteristic 0, it's always dimension 7, but for characteristic B, it depends a lot on the prime, and maybe some people will immediately see why I choose 31, because the biggest bound are for Mersenne primes, are for prime P of the type 2 to the L minus 1, which is the case of 31. In that case, the degree is 2P plus 1. But for some other primes, the degree is a lot less. So this is one example. Now, I would like to explain the linearity and nonlinearity criterion in one case, where the answer is clear. And this is theorem D. Now you assume that S, the group S, is finitely linearity. And in that case, the group hot S of A to K is linear if and only if for all the rank of lambda delta is equal to the transcendental degree of lambda delta for any delta in the projective line. So you have an exact statement. And what is the meaning? What means this condition? It means the last condition means it means there is some constant R which depends on delta of course, so that lambda is generated by element x1, xr, and theta, where x1 up to xr are algebraically independent, and zeta is a root of 1. Of course, the group itself can be torsion free, so in that case zeta equals 1. But it means that the group as such freely generated by R algebraically independent element. And when you see this criterion, of course, it's very easy to give one example, which is amazing. And now I would like to mention the example. So it's example B. And example B has two parts again. B1 says that there are co-compact lattices in SM2R such that the automorphism group of, even you can take the complex plane if you want, with isotropy S is linear over C. And B2, because I like contrasted statement, is that if S is the lattice in SM2C, by lattice I mean finite co-volume lattice, then this group, both S of A2C, is not linear. So, to finish, I would like to explain at least one proof, and I would like to explain the proof of example B1. So B1 is based on the fact that it's based on the following lemma, that there are co-compact lattices in SM2R such that the trace of H is transcendental number, transcendent for any infinite order, infinite order H in S. Of course, but this is equivalent to the fact that the eigenvalues are transcendental. And it can be done only for infinite order elements. And why it is so? Why this lemma implies what B1 is because you see, it's very easy to prove that for such lattices, by hyperbolicity, it's very clear that lambda delta has always rank less or equal than 1. So when the rank is 1, simply it means that the S delta contains an infinite order element, so it has transcendental eigenvalue. So up to some root of unity, it satisfies the level. So that's not very difficult. But now the problem is how to prove it. And this lemma is maybe well known, but I can't find the reference in the literature. But anyhow, I would like to explain the proof. So let's take integral j greater than 2, and I will denote by phi j the famous group, which is a frontal group of surfaces, of all surfaces of genus G. So it is denoted by 2G elements and only one relation. A1 to 1, A2 to 2, J to J equal 1. So parenthesis means commutators. And now instead of working with SL2R, I will do the same lemma in PSL2R. If you prove a similar statement in PSL2R, it's easy to show that. And now let me remember so what we're looking for is a space of all representation O from phi j to E S L R. And in order that it is a co-compact lattice, it should be loxodromic. And this is, and of course we can make quotient modulo PSL2. And this space is exactly one realization of the Teschmuller space. So different description, but this is one possible description. And now it turns out if you take such a rho, then you can define a surface sigma rho, which is Poincaré hyperplane modulo the action of rho J. And this, of course, is a closed surface of genus J, and it has a hyperbolic matrix which came from the Poincaré metric on H. And it turns out that if you take any gamma in J, then when you compute the trace of rho of gamma, so the trace of rho of gamma is not well defined because it's impossible. But then we take the trace of the square. So the square is a well defined element in SL2. This is exactly the hyperbolic cosinus of the length of gamma. And what I mean by this, gamma, if instead of taking gamma in Pj, I will take conjugacy class, and gamma is the same as a free orthogonal class in sigma rho, and therefore it is the same, it is represented uniquely by the closed geodesic. And this is the length of the corresponding geodesic. So what you have to do is to show that when you move in the technical space, and now I will explain the proof, but the proof will be not complete. In the technical space, so I take alpha, any element in Q bar, I take any gamma, and I can define Z gamma alpha in the set of all the rho, so that the trace of rho of gamma square equal to. So basically the idea is that, what is this? This is, in the worst case, an hypersurface. So it has a closed, so it has an empty interior, and you have only, so the Z gamma alpha are only finite, are only countably infinite number of them. So by the Ver's theorem, you see that the union of Z gamma alpha is not equal to the whole technical space, because the technical space is a map. This works, except that you need to know that the trace of rho of gamma square is not constant. Because otherwise you get the surface, but very few. And so what you have to prove is that when you move inside the technical space, the length of the geodesic is not always the same. And there is one easy case, is when you take a closed one. So you close the geodesic, everything is easy, because you know that you can pinch the closed geodesic as much as you want. You get something like this. But usually, of course, you don't have, so the length of simple geodesics can be as short as you want, but usually you have geodesics which are not simple, they intersect themselves. And what you should do for those is that if gamma is any geodesics, it's always meet a simple one. So gamma is here. No, my picture is correct, but this is gamma. And this is your closed geodesic beta. And now when you pinch this beta, you see that the color is extended. So it should be a picture of this. And so you say that you increase the size of gamma by doing this, and so the length of gamma is unbounded. If you want a closed formula, indeed there is a closed formula which says that the hyperbolic sinus of the length of gamma divided by 2 times the hyperbolic sinus of the length of beta divided by 2 is always bigger than 1. This is what is called these colors. Yeah, so the lengths are unbounded and therefore they are not constant. And so by the Ver's argument, it proves that you can find lattices where all the traces are tensor. Now I would like to mention that this is not the unique proof. There are two other proofs which are as follows. First, the proof number 2 has been shown to me by Ingrid Kirner from Sumy. And indeed, it's because the line function has some strict convexity properties along some geodesic line. So this is another way to see that. And the third proof, which was the original proof, is the following. You embed the technical space inside the character variety, which is the space of representation of Isley now, not in PSL2R, but in PSL2C. And you take the geometric quotient by PSL2C. Here we are working, this is an algebraic variety, and this is the Mech-Mat quotient. And the trick is that if rho is any representation in TFG, then it is the same component as the trivial representation. Inside the character variety. And so you see now easily that if gamma is any element in Ij, say non-trivial, so it means that you have a path in rho 0 in this characteristic variety, such that rho 0 is rho, such that rho 1 equal identity, trivial representation, and therefore you see that rho 0 of gamma takes the trace of that because it is loxodromic. It takes any value strictly bigger than 2, and so the trace of the trivial representation is of course 2. And therefore along this path, the trace function is not constant. And the last point is to prove that the trace function is not constant, is to prove that when you tensor by C the tangent space of the Teichmüller space at rho 0, this is the tangent space in the character variety at the same point. And therefore, it's implied that the Teichmüller space is Januski-Darcy. Therefore, since the function is not constant on the whole, it is not constant in the subset which is Januski-Darcy. That's the trick. And the last point to prove that it can be connected to the trivial representation, this is equivalent to a theorem by Bertz, who said that loxodromic representation can be lifted to SL2. Because the character variety for SL2 is connected. And so for PSL2C, there are two connected components. So now, since I'm in the front of the distinguished audience of Ukrainian algebraists, I would like to ask the following question. Is there a purely algebraic proof of the lemma I stated?